in the last class we looked at the Griffith's analysis. So, how if you take a member and apply a load and then hold it with the grips and then insert a slit, and as you continue to increase the length of the slit, at a particular length the slit gives through, then the crack propagates suddenly, right. So, then we have looked at the reason for creation of the surface, the energy, that is strain energy that is present in the material is released, and that is what is responsible for creation of the two new surfaces, right. And then we have looked at the condition for the safe crack, as long as the crack length AC is less than this value, where this depends on the material and surface energy and the applied load. If the slit length that you have introduced is less than this value, then the slit does not suddenly propagate or expand, but the moment this condition is not met, as soon as the length of the crack is larger than this value, then the crack suddenly jips through, right, because then you meet the condition that the energy release rate or E dEr by dA is greater than the rate of change of surface energy with respect to the crack length, right. So, when we are having a body with a crack present, the strain energy in the component can either increase or decrease depending upon the kind of boundary conditions that we have, okay, when the crack is advancing in the body. Nevertheless, whenever you are having a crack in the body, the stiffness of the body reduces. As you increase the length of the crack, the stiffness of the body reduces. That means the amount of force that is required to create unit displacement is going to go down, right. That is what we mean by stiffness. And sometimes wherever you are applying the load, so that means the point of application of the load can actually move or stay remain, right. So, when the point of application of the load is moving, that means you have work done on the system. Sometimes the point of application of load where you have applied load does not move, then there is no work done, right. And of course, when we are generating two new surfaces, that is the creation of the crack, then you are consuming some energy. That energy must be either coming from the strain energy or the external work done, or both, okay. All right. So, now we look at what do we mean by this energy release rate, a very important property of the material, a very important component that you need to be aware of whenever we are talking about crack growth in a material. So, the energy release rate usually represented by word G in honor of Griffith, right. G is energy release rate. Whenever you are in fracture mechanics class, G is your energy release rate. So, what is the definition of energy release rate? Energy release per unit increase in crack area, right. As your crack is advancing, per unit crack area. So, G is dE by dA, capital A is your crack area. So, now let us consider an incremental increase in the crack area to be delta A, right. It is an increase in the crack area, and an incremental external work will be delta W external work. So, W is your external work, increase in external work during which time the crack is propagating, that I am representing as delta W. Ext means external work that is done to create the crack extension. And now, when you are doing some work on the body, then you are obviously imparting some strain energy to the body. So, the strain energy of the body during this process increases by an amount delta U, right. Then you can actually write the balance, the energy release rate per unit area, that means G is your energy release rate, right. So, energy release per unit area times delta A will give you energy release is equal to external work minus the strain energy, right. Whatever external work that you are putting in, a part of it is going into increasing the strain energy of the body, a part of it is going to crack propagation, and that is what is responsible for this energy release. Okay. And now, if you divide the both sides with delta A and take the limit delta A tends to 0, right, then you will have what? G equal to minus d by dA u minus W external, right. There is a negative sign here, that is why so then G can be written as negative of d by dA u minus W external. The strain energy minus external work is your potential energy of the body, right. That is why, so the potential energy pi is written as strain energy minus work done. So whatever is there in this parenthesis is basically your potential energy. So you can write G equal to negative of d pi over dA. Okay, that is the definition of your, that is the relation between energy release rate and potential energy of the system, and A is your crack area. And please note that your G, energy release rate, is always positive, right. Energy release per unit area, it is always a positive quantity, and hence this d pi by dA should be a negative quantity always. So the energy is available from the system if the potential energy decreases. Only when the potential energy decreases, that is when your energy is available for crack growth. So that because G is always positive, right, because this d pi by dA quantity should be negative. That is negative means energy is actually, potential energy is decreasing. If it is increasing, then it will be positive, isn't it? So that is the condition. All right. So now let us assume a plate of uniform thickness. You are assuming a plate whose thickness is B. Then I can write potential strain energy release rate G is equal to negative 1 over B times d pi by dA, where A is your crack length. Capital A is your crack area, small a is your crack length, and B is your thickness of the body. Okay. And now let us consider the example of a DCB specimen. What do you mean by DCB specimen? Double cantilever beam. Have you heard of this specimen? It looks something like this. That is how it looks like. Okay. So we are talking about, we are taking the example of a DCB specimen with compliance approach. What do we mean by compliance approach? We will look at. So you know, if you know the compliance of the material to be C, then the displacement is equal to, let us say you are applying a load P, corresponding to that there is a displacement U, then U and P can be related by U equal to C times P. Compliance is inverse of your stiffness, isn't it? Is that clear? U equal to C times P. And now let us say you have applied constant load. The load is fixed. So then your strain energy can be written as half P times U, right? All of you agree with that? And external work is, because your load is fixed and there is a displacement associated with that load, P times U. What is our G? The definition of G? Minus d pi by dA, capital A, that is equal to minus 1 over B. So G is equal to minus 1 over B d pi by dA, right? So now I can write pi equal to, now I need to find out what is my pi, that is potential energy, that is strain energy minus external work. The strain energy is half P times U, minus external work is minus Pu, so that will be negative of half Pu, right? So now I can define my G, which is minus d pi by dA 1 over B. So wherever pi is there, I will write minus half Pu. So then d pi by dA, and then I can write this pi as P times U, right? And then I replace U with C. So I have a relation between U u equal to c times p, right? So wherever u is there, so half p times u can be now written as p by 2b times du by a. So you just plug in this guy here and then you will be able to write that. And what is du by dA? So u is equal to c by p, and a changes as a function of compliance, we know that, right? As the crack length increases, the stiffness of the material decreases. So your compliance should be dependent on your a, and hence you can differentiate c with respect to a, and that is what you will get. So your energy release rate is equal to p square by 2b times dc by dA. Is that clear or no? If it is not clear, do it. So what we have done is, what is here, load is constant, right? We said constant load. Since load is constant, I can replace P is equal to U by C, right? So then I can write 1 by B d by dA of U square by C. Is that correct? Is it not? Did I make a mistake? Because my P is a constant, and what I am writing Pu, oh sorry, d by d of Pu, C times P, U equal to C times P, and then this becomes P square. P is a constant, so it can go out. So that way it is P square by 2b times dC by dA. The fact that P is constant, I can bring it out. If P is not constant, I could not bring it out, right? Because the condition is with the constant load is what we are trying to do. So my G, when I have a constant load, is given by P square by 2b times dC by dA. Okay? Now if I fix the displacement, now I am not fixing the load, but I am fixing the displacement. Fixed grip means the displacement is fixed. That means U is constant, and as the crack advances, your P changes, isn't it? Because the reaction force is changing. So can you actually find the expression for G when you have fixed grip? Can I erase this part? Let me erase. So when we have fixed grip, what happens? What happens to my U and what happens to my W? What is my W when we have fixed grip? What do you mean by fixed grip? The point is not moving, right? You are holding the displacement. That means wherever you are applying the load, the position at which you are applying the load, that is fixed in space. That means there is no displacement associated with that force. That means what is the work done? Work done is 0, and hence U equal to half Pu. That means pi equal to half Pu, right? Because this guy is 0, so U equal to half Pu is same. So pi equal to U minus W external, so pi equal to half Pu, right? Then G equal to minus 1 by 2b d by dA of Pu, right? Now here what is constant? Displacement is constant, not the force. If the displacement is constant, we should write displacement in terms of force, right? So do that. Did we do the same thing or what? Wait a moment, I think I made a mistake somewhere. Yeah, minus is there. Yeah, displacement is constant. So, P should be written in terms of the displacement, because we have to find the derivative with respect to P. So, I can write P equal to U by C. So, everything instead of having it in terms of U, so in terms of P, I am writing P is in terms of U by C. So, that is equal to minus 1 by 2B d by dA times U square by C. Agreed? Is that clear or not? Change in displacement is 0. For you have applied some displacement and then you are holding there. So, the initial strain energy that you are putting in is half Pu, right? And the U is not changing afterwards. So, you have a body, okay? To this body you have applied some displacement, and there you are holding, that means there you are at that displacement you are fixing. That is what you mean by fixed grip experiment. So, imagine that now you have this body, you are holding at that displacement, and now you have a crack. If you are not changing the displacement, as the crack propagates, what happens to the force? So, when you are holding at this particular position, there will be some reaction force at this position, right? Here you are prescribing displacement. So, at the ends you will have reaction force, and as the crack is extending, what happens to that reaction force? It reduces, because the stiffness is reducing. In the previous case, what happens? You are applying a constant force, you have applied some force, you got some displacement, and you are maintaining the force same. You are maintaining the force same. So, when you are maintaining the same force and the crack is propagating, what will happen to displacement? Displacement, what happens? Increases or decreases? Increases, because for the same force, your stiffness of the component is decreasing as you are increasing the crack length. Alright? Clear? What is? Compliance is opposite of stiffness. Stiffness is force power displacement, right? Compliance is reciprocal of that. You can see here, C is your compliance, right? C is displacement by force. Alright. So, now what will be this one? So, as your crack length is changing here, will U change? U is fixed grip, U is not changing. So, U can be brought out or not? Can I bring U out? So, minus U square by 2B d by dA of 1 by C, that is d by dA of 1 by C will be what? Minus 1 by C square dC by dA, isn't it? So, minus 1 by C square. Agreed? So, what is C? So, this negative becomes positive. So, U square by 2B times C square is U square by P square. So, P square go to the numerator, U square go to the denominator, dC by dA. So, U square gets cancelled. Therefore, so now I can write my G equal to P square by 2B dC by dA, right? Whether I do constant grip or constant force, my G gives me the same formula for this particular case. So, that is P square by 2B times dC by dA. That is my energy release rate for a double cantilever beam problem. Like that, if you are given any other problem, you should be able to calculate what is my energy release rate. Is that clear? So, this formula and this formula are the same. So, for a DCB specimen with one cantilever end attached to a fixed jaw, that means the left hand side is fixed of a tensile machine, the deflection of the moving jaw is twice that of the cantilever end, right? Because you have double cantilever. If you are you have fixed this to one end, other end you are pulling. So the displacement what we are talking about is the twice the displacement, right, because you have two cantilevers. This is one unit, this is another unit, both of them are moving symmetrically. The displacement, total displacement is twice that of the single cantilever displacement. So if you have a cantilever with an end load, what is the deflection of the cantilever? PL cube by 3EI, right? Yes or no? So imagine in this cantilever, let us say the double cantilever what we are talking about. So it is like it is fixed here, right? There may be bond here, but you can see that this is like a fixed end. Then this is your A. This is your crack length. Can you see that? If that is the crack length, this displacement and this force if P, then this displacement will be PA cube by 3EI. But you have two cantilevers, the total displacement will be 2 times PA cube by 3EI, right? And then the compliance will be U by P. So the compliance is 8A cube by 3B H cube. Then you can calculate what is your dC by dA. What is your dC by dA? Is 24A square by EBH cube. You just have to find the derivative of this guy. And then G can be written as P square by 2B dC by dA, that is 12A square P square by EB square H cube. That is the energy release rate of a double cantilever beam whose length, the crack length, initial crack length is A and applied load is P, elastic modulus E is B, E, outer plane thickness is B, H is what? That is your H, right? Alright. Please note that I have put 1 here. What is the reason for that 1? That is what is called mode 1 energy release rate, because it is an opening mode, right? The loading, we have seen 3 different kinds of modes: mode 1 fracture, mode 2 fracture and mode 3 fracture. Here it is a clearly opening mode and hence it is written as G1. So now you can actually, if you know so this is a problem wherein all the other dimensions are given and you are required to calculate the energy release rate. Determine the critical energy release rate of a DCB specimen loaded in a tensile testing machine. The thickness of the specimen is 30 mm, depth of each cantilever is 20 mm, crack length is 50 mm, it is made of a hardened steel and the crack is about to propagate. That means this is the load at which the crack is ready to propagate. So he is asking you to create, the problem asks you to calculate critical energy release rate. Please pay attention here. G1, whatever you have calculated here, is energy release rate. And this is dependent on the load that you apply, geometry of the body and the crack length. For any given load, you have some energy release rate. But when does the crack propagate? The crack starts propagating when the energy release rate in the material becomes equal to the critical energy release rate of the material. Critical energy release rate is a property of the material. Energy release rate is the response of the material to the applied load due to its geometry and applied load. So when G1 becomes equal to G1C, this is what is called critical energy release rate. This is a material property. For each material you will have a critical energy release rate. And it is G1C, that means mode 1 critical energy release rate. If the same material, if it is loaded in mode 2, the critical energy release rate in mode 2 will not be same as the critical energy release rate in mode 1. So the energy release rate, critical energy release rate depends on the type of mode or mode of fracture. That is important to know. Okay. So here he is saying that this is the force at which the material is about to give in. That means that is your critical energy release rate. That is why the question asks you to calculate critical energy release rate, because that is when the crack is ready to grow. You can plug in these numbers and you will be able to figure out what this number is. What is the unit of energy release rate, by the way? What is the definition of energy release rate? How did we define energy release rate? Joule per meter square, because energy released per unit area of the crack. So it is not watts. If you think energy released per unit time, it is watt, right? It is not watt, it is joule per meter square.